Tonight, we're going to go inside the densest object you can still see in the universe, a neutron star. You've probably heard that neutron stars are incredibly dense, but here's what most people never think about. The matter inside a neutron star isn't like anything that exists anywhere else. Atoms themselves cannot survive in there. They get crushed out of existence. What replaces them is something so strange, so alien, that physicists still argue about what it actually is. Because as you go deeper and deeper into a neutron star, layer by layer, matter transforms into forms that might not exist anywhere else in the entire cosmos. And the deepest core might contain something we've never even imagined. By the end of tonight, you'll understand why the inside of a neutron star is one of the biggest unsolved mysteries in all of physics. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you understand. Matter. The stuff everything is made of. You, the chair you're sitting in, the air you're breathing, the planet beneath your feet. All of it is made of atoms. And atoms have a very specific structure that you probably learned about in school. At the center of every atom is a nucleus, a tiny dense core made of protons and neutrons packed tightly together. Orbiting around that nucleus at relatively enormous distances are electrons. These electrons form a cloud around the nucleus, and that cloud defines the atom's size. Here's something most people don't appreciate. Atoms are almost entirely empty space. The nucleus is incredibly small compared to the atom as a whole. If you could blow up an atom to the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. The electrons would be like gnats buzzing around the upper seats. Everything in between would be nothing. Just empty space. This means that you, sitting there right now, are mostly nothing. The chair you're sitting on is mostly nothing. The ground beneath you is mostly nothing. Every solid object you've ever touched, every wall you've ever leaned against, every rock you've ever picked up, all of it is overwhelmingly empty space. You don't fall through the floor, not because matter is solid in the way you think it is, but because of electromagnetic forces between the electron clouds of atoms. The electrons in your shoes repel the electrons in the floor. It's a force field, not a physical barrier. This arrangement of matter, nuclei surrounded by electron clouds, with vast empty space in between, works perfectly well under normal conditions. It works on Earth. It works on the Moon. It works on Jupiter. It works inside the Sun, though in the Sun, the atoms are ionized, meaning the electrons have been stripped away by the intense heat. But the nuclei are still intact. Protons and neutrons are still bound together in their normal configurations. Even inside a white dwarf, the incredibly dense remnant left behind when a star like our sun dies, atoms are crushed but not destroyed. In a white dwarf, electrons are squeezed into the smallest possible space allowed by quantum mechanics. The star is held up by something called electron degeneracy pressure, which is essentially the refusal of electrons to be pushed into the same quantum state. But the nuclei themselves remain intact. Battered and compressed, yes, but still recognizable as atomic nuclei, carbon nuclei, oxygen nuclei, the products of the star's former nuclear fusion. They're still there, still themselves, but there is a threshold, a line beyond which even this arrangement breaks down completely, a point where gravity becomes so overwhelming that atoms simply cannot exist anymore. And that threshold is what creates a neutron star. When a massive star, one significantly heavier than our Sun, reaches the end of its life, it runs out of fuel. Throughout its lifetime, the star has been performing a delicate balancing act. The outward pressure from nuclear fusion in the core pushes against the inward pull of gravity. Fusion pushes out. Gravity pulls in. As long as those two forces balance, the star is stable. It can shine for millions of years in this equilibrium, but fusion requires fuel. The star starts by fusing hydrogen into helium in its core. When the hydrogen runs out, gravity compresses the core further, raising the temperature until helium can fuse into carbon and oxygen. When the helium runs out, gravity compresses again, and carbon fuses into heavier elements. This process continues, building up layers like an onion. Hydrogen burning in the outermost shell, then helium, then carbon, then neon, then oxygen, and finally silicon in the innermost shell. Each successive fuel burns faster than the last. Hydrogen fusion can sustain a star for millions of years. Helium fusion lasts maybe a few 100,000 years. Carbon burning lasts perhaps a few thousand years. When the star reaches silicon fusion in its core, it's in its final days. Silicon fusion lasts only about 1 day. 1 single day. After millions of years of life, the star's final act of fusion is over in 24 hours. And silicon fusion produces iron. This is where everything goes wrong. Iron is the end of the line for nuclear fusion. Every element lighter than iron releases energy when you fuse it into something heavier. That released energy is what powers the star and holds it up against gravity. But iron is different. Fusing iron into anything heavier doesn't release energy. It requires energy. It takes energy away from the star instead of providing it. So when the core fills with iron, fusion stops. And when fusion stops, there's nothing left to push outward against gravity. The balance that sustained the star for millions of years is suddenly gone. Gravity wins. What happens next occurs in less than a second. The iron core, which is roughly the size of Earth at this point and contains about 1.4 times the mass of our Sun, collapses. It doesn't collapse slowly. It collapses at speeds approaching a quarter of the speed of light. About 75,000 kilometers per second. The entire core of a massive star, a sphere roughly the size of our planet, implodes in a fraction of a second. Try to picture this. An object the size of Earth containing more mass than the Sun, falling inward at 75,000 kilometers per second. The amount of energy involved is almost beyond calculation. The gravitational potential energy released during this collapse is about 300 times more than the energy our Sun will produce over its entire 10 billion year lifetime, and nearly all of it is released in about 10 seconds. During this collapse, something extraordinary happens to the matter in the core. As the density increases, the atoms are squeezed together harder and harder. In normal matter, atoms maintain their structure because electron clouds keep nuclei separated. But as the pressure mounts during the collapse, the electrons are squeezed closer and closer to the nuclei. At first, the matter behaves like it does in a white dwarf. Electrons resist being pushed together. Electron degeneracy pressure fights back against gravity. But in a white dwarf, this pressure is enough to stop the collapse. In a collapsing stellar core, it's not. The gravity is simply too strong. The mass is too great. Electron degeneracy pressure fails, and when it fails, something remarkable happens. The electrons are forced directly into the protons in the nuclei. When an electron meets a proton under these extreme conditions, they combine through a process called inverse beta decay. The electron and proton merge to produce a neutron and a neutrino. The neutrino escapes, carrying away energy. The neutron remains behind. This is the moment atoms die. This isn't a metaphor. This isn't poetic language. The atomic structure that defines virtually all the matter you've ever encountered simply ceases to exist. Protons and electrons, the charged particles whose electromagnetic interactions create everything we recognize as chemistry, as solid matter, as the physical world, they merge and become something else. They become neutrons, neutral particles with no electric charge. And without electric charge, there's no electromagnetic repulsion to maintain atomic structure. There are no electron clouds. There are no orbits. There are no atoms. There is only nuclear matter. Dense, neutral, featureless nuclear matter made almost entirely of neutrons. The transformation is total. Before the collapse, the core contained iron atoms, each one a complex structure with 26 protons, roughly 30 neutrons, and 26 electrons arranged in specific energy levels. After the collapse, all of that structure is gone. The protons have absorbed the electrons and become neutrons. The individual nuclei have dissolved into a continuous sea of neutrons. The identity of every atom has been erased. It no longer matters that the matter was once iron, or silicon, or carbon, or oxygen. All of those identities required atomic structure to exist. Without atoms, there are no elements. There is just nuclear matter. Let me try to convey the density involved, because this is where human intuition completely fails. The density of water is 1 gram per cubic centimeter. That's the baseline most people are familiar with. If you've ever held a liter of water, you've held 1 kilogram of matter in a volume of 1,000 cubic centimeters. Rock is denser, typically about 2 to 3 grams per cubic centimeter. Iron is about 8 grams per cubic centimeter. Lead is about 11 grams per cubic centimeter. Gold is about 19 grams per cubic centimeter. These are the densest materials most people encounter in everyday life. Even the densest naturally occurring element, osmium, is only about 22.5 grams per cubic centimeter. Now, a white dwarf has a density of about 1 million grams per cubic centimeter. That's already staggering. A teaspoon of white dwarf material would weigh about 5 tons on Earth. You couldn't lift it. You couldn't budge it. 5 tons in a volume smaller than the tip of your finger. But a neutron star makes a white dwarf look like a cotton ball by comparison. The average density of a neutron star is about 400 trillion grams per cubic centimeter. Let me say that again because the number is so extreme, it's easy to let it slide past without really registering. 400 trillion grams per cubic centimeter. 400 million grams in a space the size of a sugar cube. A teaspoon of neutron star material would weigh about 6 billion tons. 6 billion tons. That's roughly the weight of every single human being on Earth, combined, compressed into a space smaller than the last joint of your little finger. Or think of it this way. If you could somehow scoop up a teaspoon of neutron star material and place it on the surface of Earth, it would weigh more than Mount Everest. Actually, significantly more than Mount Everest. Mount Everest has an estimated mass of about 810 trillion grams. A teaspoon of neutron star material, depending on exactly where in the star you scoop from, could weigh several times that. A teaspoon heavier than the tallest mountain on Earth. Try another comparison. The Great Pyramid of Giza has a mass of about 6 million tons. A teaspoon of neutron star material weighs 1,000 times more than the Great Pyramid. 1,000 Great Pyramids compressed into a teaspoon. Or try this. All the water in all the world's oceans has a mass of about 1.4 times 10 to the 21st grams. A cubic meter of neutron star material would weigh about 400 trillion grams times 1 million cubic centimeters per cubic meter, which comes to about 4 times 10 to the 20th grams. That's roughly a third of the mass of all Earth's oceans packed into a single cubic meter. A box about the size of a washing machine containing a third of the mass of every ocean on the planet. These numbers become so extreme that they stop being quantities you can comprehend and start being more like mathematical curiosities. Your brain can process the words, you can understand the arithmetic, but you cannot truly picture what it means for matter to be this dense. Nothing in your experience, nothing in anyone's experience, corresponds to matter at these densities, and yet neutron stars exist. They're real physical objects. There are estimated to be hundreds of millions, possibly up to 1 billion of them in our galaxy alone, and every single one of them is made of matter in this almost incomprehensible state. Now, when the collapsing stellar core reaches these densities, something stops the collapse. The neutrons, like electrons before them, obey the rules of quantum mechanics. Specifically, they obey something called the Pauli exclusion principle, which says that no two identical fermions can occupy the same quantum state at the same time. Neutrons are fermions. When they're packed this tightly, they resist being compressed further because they'd have to occupy the same quantum state, which the laws of physics won't allow. This resistance is called neutron degeneracy pressure, and it's what holds a neutron star up against gravity. It's not heat, it's not fusion, it's not radiation. It's a quantum mechanical effect, a fundamental property of how matter behaves at the subatomic level. The neutrons literally cannot be squeezed any closer together without violating the laws of quantum mechanics. At least that's the simplified version. The reality is more complicated, which we'll get to later. But the key point is this: neutron degeneracy pressure stops the collapse. The infalling matter hits the newly formed neutron core and bounces. That bounce, combined with a flood of neutrinos pouring out of the core, drives the outer layers of the star outward in a catastrophic explosion, a supernova. The supernova is one of the most energetic events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The explosion scatters the outer layers of the star into space at speeds of thousands of kilometers per second. These expanding clouds of gas contain all the heavy elements the star forged during its lifetime: carbon, oxygen, silicon, iron, and even heavier elements created in the explosion itself. These elements will eventually mix with interstellar gas and be incorporated into new stars and planets. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged inside a star that exploded before our sun was born. But behind the explosion, the core remains. A sphere of neutron-rich matter about 12 to 13 kilometers across, roughly the width of a mid-sized city. And in that tiny sphere is packed between about 1.5 and 2 times the mass of our sun. This is a neutron star. And what's inside it is unlike anything else in the observable universe. Think about what we've just described. A sphere smaller than most major cities that contains more mass than the sun. The sun is 864,000 miles across. The neutron star is about 8 miles across. The Sun's volume could contain about 1.3 million Earths. The neutron star's volume is about the same as a large asteroid. And yet, the neutron star is heavier than the Sun. This compression has consequences beyond just density. The gravity at the surface of a neutron star is about 200 billion times stronger than gravity on Earth's surface. If you could somehow stand on the surface of a neutron star, which you obviously cannot, you would be instantly crushed into a thin film of atoms. Actually, you wouldn't even get close. Long before you reach the surface, the tidal forces would tear you apart. The difference in gravitational pull between your head and your feet would be so extreme that your body would be stretched into a long, thin strand, a process physicists grimly call spaghettification. Even light is affected by this gravity. Light leaving the surface of a neutron star is redshifted, meaning its wavelength is stretched by the effort of climbing out of the gravitational well. Photons leaving the surface lose about 20 to 30% of their energy just escaping. Space itself is warped around a neutron star. If you could see one up close, the curvature of space would allow you to see more than half of the star's surface at once, because light bends around it. The backside of the star would be partially visible, because photons emitted from the far side curve around the star's extreme gravitational field and reach your eyes. You would see a sphere that appears strangely swollen, as if more of its surface is visible than geometry should allow. The escape velocity at the surface of a neutron star is about 100,000 to 150,000 kilometers per second. That's roughly a third to half the speed of light. To leave the surface of a neutron star, you would need to be traveling at a significant fraction of light speed. By comparison, the escape velocity from Earth's surface is only about 11 kilometers per second. You need to go about 10,000 times faster to escape a neutron star than to escape Earth. The magnetic field of a typical neutron star is also extraordinarily powerful. A normal neutron star has a magnetic field of about 10,000 to 100 million Tesla. Earth's magnetic field, by comparison, is about 25 to 65 millionths of a Tesla. The magnetic field of a neutron star is roughly 1 billion times stronger than Earth's, and some neutron stars called magnetars have magnetic fields 1,000 times stronger still, reaching up to about 100 billion Tesla, making them the most powerful magnets in the known universe. But right now, we're not concerned with the spin or the magnetism of neutron stars. We're concerned with what they're made of. Because the matter inside a neutron star is not a uniform blob of identical neutrons. It has structure, it has layers, it has regions where the physics changes as you go deeper, where the density increases and matter takes on increasingly exotic properties. In fact, a neutron star might be the most complex object in the universe in terms of the range of physical states it contains. From its surface to its core, a neutron star takes you on a journey through states of matter that range from something almost recognizable at the very top to something utterly unknown at the very bottom. The outer surface, the thin atmosphere and outermost crust is made of something not too different from the matter, actual atomic nuclei with actual electrons. But as you descend, layer by layer, the matter transforms. Nuclei become swollen with extra neutrons. Then neutrons begin leaking out of the nuclei entirely. Then the nuclei dissolve altogether into a continuous fluid of neutrons. And then, at the very center, in the innermost core where the density reaches its peak, something else might happen. something physicists can't yet describe with certainty. The matter might become a superfluid. It might contain exotic particles called hyperons. The neutrons themselves might dissolve into their constituent quarks, creating a state of matter that hasn't existed freely in the universe since the first microsecond after the Big Bang. We don't know. And that uncertainty, that gap in our knowledge, is one of the most fascinating frontiers in all of physics. The inside of a neutron star is a laboratory for extreme physics that we can never build on Earth. The densities at the core of a neutron star are 5 to 10 times higher than the density of an atomic nucleus, which is already the densest form of matter we can study in our particle accelerators. We can smash atomic nuclei together at nearly the speed of light in facilities like the Large Hadron Collider at CERN, and we can briefly create tiny volumes of extremely dense, extremely hot matter. But this matter is hot, trillions of degrees hot. The matter in a neutron star's core is cold by comparison, not cold by human standards, obviously. The interior temperature of a neutron star is still about 100 million to a billion degrees, but in nuclear physics terms, that's cold. The thermal energy of the particles is much less than their Fermi energy, the quantum mechanical energy that comes from being squeezed together. The neutron star is cold, dense, and in equilibrium. That combination, extreme density but relatively low temperature, is something we simply cannot reproduce in any laboratory on Earth. We can make matter hot and dense for a split second in a particle collider. Or we can study matter that's cold, but at normal densities, but cold and ultra-dense at the same time, sustained for millions of years. That's something only a neutron star can do. This is why neutron stars matter so much to physicists. They're natural laboratories for testing our theories of how matter behaves under the most extreme conditions imaginable. The equations that describe matter at these densities, what physicists call the equation of state, determine everything about a neutron star. How large it is, how massive it can be, how it cools, how it vibrates, how it responds to disturbances. If we can figure out what neutron stars are made of, if we can determine the equation of state for ultra-dense matter, we'll have learned something fundamental about how the universe works at its deepest level. And right now, as of the 2020s, we're closer to answering this question than we've ever been. Gravitational wave observations from merging neutron stars, precise measurements of neutron star masses and radii from X-ray telescopes, and advances in nuclear theory are all converging to constrain what the inside of a neutron star can be. But the answer isn't in yet. The core of a neutron star remains one of the great mysteries. So let's go inside. Let's take this journey layer by layer from the surface down to the center. Let's see what matter becomes when atoms can no longer exist. Let's find out what happens when you keep squeezing and squeezing and squeezing, pushing matter into states so extreme that the physics itself becomes uncertain. It starts at the surface, a thin, hot atmosphere only a few centimeters thick. Beneath that, a crust of crystallized nuclei and electrons. Below the crust, a transition zone where nuclei become strange, distorted shapes. And then the core, a vast ocean of neutrons. And at the very center, something unknown, something that might reshape our understanding of matter itself. That's where we're going next. Now let's go to the surface. Because even though we've talked about how atoms get crushed out of existence inside a neutron star, the story isn't that simple. The destruction of atoms doesn't happen all at once. It happens gradually, layer by layer, as you descend from the surface toward the center. And the outermost layers of a neutron star are surprisingly familiar, almost ordinary, at least compared to what lies beneath. The very outermost layer of a neutron star is its atmosphere. And yes, neutron stars have atmospheres. This might seem strange for an object with surface gravity 200 billion times stronger than Earth's, but think about it. A neutron star is born in the violence of a supernova explosion. Not all of the star's material gets ejected. Some gas falls back onto the newly formed neutron star. Additionally, neutron stars can accumulate material from the interstellar medium or from a companion star if they're in a binary system. This material settles onto the surface, forming a thin atmosphere. But thin doesn't begin to describe it. The atmosphere of a neutron star is typically only a few centimeters to maybe a meter thick. On Earth, the atmosphere extends hundreds of kilometers above the surface. On a neutron star, the entire atmosphere is thinner than the height of a doorknob. The gravity is so crushingly strong that any gas is compressed into an incredibly thin, incredibly dense layer hugging the surface. This atmosphere is usually made of the lightest elements available, primarily hydrogen and helium. Light elements float to the top because even in the extreme gravity of a neutron star, buoyancy still works. Heavier elements sink. If the neutron star has been accreting material from a companion star, there might also be carbon and oxygen in the atmosphere. The composition matters because it affects how the neutron star radiates energy, which in turn affects what we observe with telescopes. When astronomers point X-ray telescopes at neutron stars, what they see is light coming from this thin atmosphere. The atmosphere acts as a filter, shaping the spectrum of radiation that reaches us. By studying this spectrum, astronomers can infer properties of the neutron star, its temperature, its surface gravity, even its radius. These measurements are crucial because they help constrain what the interior might be made of. The temperature at the surface of a neutron star is typically between 500,000 and a few million degrees. That sounds extraordinarily hot, and it is by any human standard. But remember, the interior of the star can be hundreds of millions or even a billion degrees. The surface is actually the coolest part of the neutron star, relatively speaking. It's still hot enough that the surface glows in X-rays rather than visible light. If you could somehow look at a neutron star with your naked eyes from a safe distance, it might appear as a faint blue-white point. But most of its radiation is in the X-ray part of the spectrum, invisible to human eyes. Beneath the atmosphere lies the outer crust, and this is where things start to get genuinely interesting. The outer crust extends from just below the atmosphere down to a depth of a few hundred meters. In this region, the density increases from about 1 million grams per cubic centimeter at the top to about 400 billion grams per cubic centimeter at the bottom. This is still far less dense than the neutron star's average, but it's already millions of times denser than the densest materials on Earth. In the outer crust, matter is organized in a way that's actually somewhat recognizable. There are atomic nuclei and there are electrons. The nuclei are arranged in a crystalline lattice, a regular repeating structure similar to how atoms are arranged in a metal or a salt crystal here on Earth. If you could somehow zoom in and look at the outer crust of a neutron star, you'd see a rigid crystal grid of nuclei surrounded by a sea of free electrons flowing between them, almost like the electrons in a metal conductor. But these aren't ordinary nuclei. At the surface, where the pressure is lowest, The nuclei might be iron, similar to what you'd find in the core of a white dwarf. Iron 56, with 26 protons and 30 neutrons, is one of the most stable nuclear configurations in nature. But as you move deeper into the crust, as the pressure increases, the nuclei change. They become neutron-rich. The intense pressure forces electrons to combine with protons through the same inverse beta decay process we talked about earlier, converting protons into neutrons. But unlike in the deep interior, where this process destroys atoms entirely, here in the crust, it happens gradually. The nuclei absorb the extra neutrons and become isotopes that don't exist naturally on Earth. At normal pressures, an iron nucleus has 26 protons and about 30 neutrons. But deeper in the neutron star crust, you'd find nuclei with 26 protons and 40 neutrons, then 50 neutrons, then 60. These are isotopes so neutron-rich that they'd be wildly unstable under normal conditions. On Earth, if you somehow created a nucleus with this many extra neutrons, it would decay in a fraction of a second, shedding neutrons until it reached a more balanced configuration. But inside the neutron star's crust, the immense pressure stabilizes these exotic nuclei. They can't decay because there's nowhere for the extra neutrons to go. The surrounding matter is already so dense that there's no room. The pressure forces these bloated, neutron-heavy nuclei to exist whether they want to or not. As you continue descending through the outer crust, the nuclei become more and more neutron-rich. The crystal lattice remains. The structure is still orderly, still regular, still recognizable as a solid. But the nuclei sitting at each lattice point are becoming stranger and stranger, more swollen with neutrons, more unlike anything that exists in any laboratory on Earth. The electrons flowing between these nuclei are also unusual. At these densities, the electrons are what physicists call relativistic. They're moving so fast that Einstein's theory of special relativity becomes important. Their speeds approach a significant fraction of the speed of light. These aren't the electrons you learned about in chemistry class, lazily orbiting nuclei in well-defined shells. These are ultra-fast particles screaming through a crystal of exotic nuclei at nearly light speed. The electron sea provides a significant contribution to the pressure that holds the outer crust up against gravity. Then you reach a boundary. A threshold so important that it has a specific name. It's called the neutron drip line. And crossing this boundary changes everything about how matter is organized inside the star. The neutron drip line occurs at a density of about 400 billion grams per cubic centimeter, roughly a few hundred meters below the surface. At this point, the nuclei have become so bloated with neutrons that they literally cannot hold any more. The neutrons start leaking out, dripping out of the nuclei like water from an overfilled sponge. Below the neutron drip line, you enter the inner crust. And the inner crust is unlike anything above it. In the inner crust, you have three components coexisting. First, there are still nuclei, but they're enormous and grotesquely neutron-rich, containing perhaps 150 or more neutrons each. Second, there's still a sea of relativistic electrons. But now there's a third component, free neutrons. Neutrons that aren't bound to any nucleus. They've dripped out and they fill the spaces between the nuclei like a gas or a fluid. This is a state of matter that exists nowhere else in the known universe except inside neutron stars. You have crystalline nuclear matter, a lattice of gigantic exotic nuclei, immersed in a fluid of free neutrons and a gas of ultra-fast electrons. 3 different forms of matter occupying the same space. It's like having ice cubes floating in water, except the ice cubes are nuclei, the water is a neutron fluid, and the whole thing is permeated by an electron gas moving at nearly the speed of light. As you go deeper into the inner crust, the proportion changes. Near the top of the inner crust, most of the matter is still in the nuclei. The free neutron fluid is sparse, a thin gas filling the spaces between the lattice points. But as you descend and the density increases, more and more neutrons drip out of the nuclei. The neutron fluid becomes denser. The nuclei become larger and more neutron-rich, but they're also contributing a smaller fraction of the total matter. The free neutron fluid is taking over. And here's where something truly bizarre happens. As the density continues to increase, the nuclei don't just get bigger, they change shape. Under normal conditions, atomic nuclei are roughly spherical. The strong nuclear force, which holds protons and neutrons together, pulls them into a compact ball. The sphere is the most efficient shape, minimizing the surface area for a given volume, which minimizes the surface energy. But deep in the inner crust, the competition between nuclear forces and the surrounding neutron fluid changes the energy calculations. The nuclei are so large and so close together that their shapes begin to deform. Spheres become less energetically favorable than other configurations. The nuclei elongate, merge, and rearrange into shapes that physicists have given a wonderfully ordinary name. They call them nuclear pasta. Nuclear pasta. It sounds almost comical, and the naming was intentional, because the shapes that nuclear matter takes on at these densities bear a striking resemblance to types of Italian pasta. And the names follow accordingly. At a density of about 100 trillion grams per cubic centimeter, the spherical nuclei begin to elongate into cylindrical shapes. These are called spaghetti, long tubes of nuclear matter extending through the neutron fluid. Each tube is only about 10 to 20 femtometers across, roughly the diameter of a large atomic nucleus, but they extend in long strands through the crust. Go a little deeper, increase the density a bit more, and something else happens. The spaghetti strands merge together into flat sheets. These sheets are called lasagna. They're slabs of nuclear matter separated by layers of neutron fluid. Imagine alternating layers of nuclear material and neutron fluid stacked on top of each other, like the layers in an actual lasagna. Deeper still, and the geometry inverts. Instead of nuclear matter forming sheets separated by neutron fluid, you get neutron fluid forming tubes passing through a continuous matrix of nuclear matter. These are called anti-spaghetti or bucatini, after the hollow pasta tube. The structure has flipped. What was once isolated nuclei swimming in a sea of neutrons has become a continuous nuclear medium, with tunnels of neutron fluid running through it. Even deeper, just before the crust gives way to the core entirely, you get spherical bubbles of neutron fluid embedded in a continuous nuclear medium. These are sometimes called anti-gnocchi, or Swiss cheese. The geometry is now the complete reverse of what existed at the top of the crust. Up there, you had spherical nuclei in a sea of electrons and neutrons. Down here, you have spherical holes in a sea of nuclear matter. This sequence of shapes, from spheres to spaghetti to lasagna to bucatini to Swiss cheese, represents one of the most remarkable predictions in nuclear astrophysics. It arises from the competition between the strong nuclear force, which tries to clump nuclear matter together, and the Coulomb force, the electromagnetic repulsion between protons, which tries to push nuclear matter apart. At each density, the shape that minimizes the total energy is different, and the progression follows this beautiful geometric sequence from one topology to the next. Let me slow down here because this geometric inversion is one of the most extraordinary things in all of physics. Think about what's actually happening. At the top of the inner crust, you have the familiar picture. Distinct objects, nuclei, sitting in a background medium of neutron fluid. The nuclei are the stuff. The neutron fluid is the space between the stuff. This is how we normally think about matter. Distinct things embedded in a surrounding environment. Grains of sand in water, planets in space. But as you go deeper, the balance shifts. The nuclei grow. The spaces between them shrink. The nuclei merge into rods, then into sheets. And then something profound happens. The figure and the ground switch places. What was the object becomes the background. What was the background becomes the object. The nuclear matter, which started as isolated spheres floating in a neutron sea, becomes the continuous medium. And the neutron fluid, which started as the surrounding ocean, becomes the isolated pockets, the bubbles, the tunnels drilled through a solid block of nuclear material. If you were an imaginary ant walking on the surface of a nucleus near the top of the inner crust, you'd be on an island. You could walk all the way around and come back to where you started, but you'd never reach another nucleus without crossing the neutron sea. By the time you reach the spaghetti phase, those islands have connected into long bridges. In the lasagna phase, they've merged into vast continents. And in the anti-spaghetti phase, the continents have merged into a single global landmass. And what used to be the ocean has become isolated lakes and rivers running through solid ground. The entire relationship between matter and not matter has flipped. This kind of topological transition is unique to the crusts of neutron stars, and it happens across a depth of perhaps only a few hundred meters. In a span you could walk in a few minutes on Earth, matter undergoes a fundamental rearrangement of its geometric identity. The inside becomes the outside. The figure becomes the ground. Now, I should be honest about something. As of right now, nuclear pasta has never been directly observed. We can't see inside a neutron star. We can't send a probe. We can't drill into the crust. Nuclear pasta is a prediction of theoretical models, the result of sophisticated computer simulations that model the behavior of nuclear matter at these densities. Different research groups using different computational methods have consistently found the same pasta phases, which gives physicists confidence that the prediction is robust. But it remains a prediction, not a confirmed observation. There are, however, indirect ways to test whether nuclear pasta exists. One approach involves studying how neutron stars cool. The structure of the crust affects how heat flows through it. Nuclear pasta, with its complex geometry, would scatter the particles that carry heat, slowing down the cooling process. By comparing observed neutron star cooling rates with theoretical models that include or exclude pasta phases, astronomers can test whether pasta is needed to explain the observations. So far, the results are suggestive but not conclusive. Another approach involves gravitational waves. When neutron stars spin, if their crust has irregularities, bumps, or mountains, the spinning star emits gravitational waves. The strength of these gravitational waves depends on how large the irregularities can be, which depends on how strong the crust is. And the strength of the crust depends on its composition and structure. including whether nuclear pasta is present. This brings us to one of the most remarkable properties of nuclear pasta. If it exists, it might be the strongest material in the universe. Computer simulations suggest that nuclear pasta can withstand stresses roughly 10 billion times greater than steel. The breaking strain of nuclear pasta, the amount you can deform it before it fractures, is estimated at about 1/10. That means you could stretch it by about 10% before it breaks. Steel breaks at a strain of less than 1%. Nuclear pasta is not only much stronger in absolute terms, it's also much more deformable. It can bend and flex without breaking. It's both incredibly strong and remarkably elastic. This has implications for how large the mountains on a neutron star can be. When I say mountains, I don't mean anything you'd recognize as a mountain. The surface of a neutron star is incredibly smooth. The strongest gravity in the universe flattens everything. A mountain on a neutron star might be only a few centimeters tall at most. Maybe a millimeter? Maybe less? But even a mountain, a fraction of a millimeter tall, on a spinning neutron star would create a slight asymmetry. A tiny bump that would cause the star to emit gravitational waves as it spins. The height of the tallest possible mountain depends on the breaking strain of the crust. If the crust includes nuclear pasta, mountains could be slightly taller and the gravitational wave emission slightly stronger. Gravitational wave detectors like LIGO and Virgo haven't yet detected continuous gravitational waves from spinning neutron stars. But the upper limits they've set are beginning to constrain the crust's strength, and by extension, the possible existence and properties of nuclear pasta. We're not there yet, but we're getting closer to testing this prediction observationally. The inner crust, this entire region of dripped neutrons and nuclear pasta, extends from the neutron drip line down to where the density reaches about 130 trillion to 200 trillion grams per cubic centimeter. At this point, the individual nuclei, whatever exotic shape they've taken, can no longer maintain their identity. They dissolve. The distinction between nuclear matter and free neutron fluid disappears. Everything merges into one continuous fluid of nuclear matter. You've reached the core. But before we go there, let me pause and emphasize something about the crust as a whole. The entire crust of a neutron star, from the atmosphere to the bottom of the pasta layer, is only about 1 to 2 kilometers thick. 1 to 2 kilometers. On a neutron star that's about 12 kilometers in radius, the crust is a thin shell making up maybe 10 to 15% of the radius, and only a few percent of the total mass. Think about that. Everything we've discussed so far, the atmosphere, the outer crust with its crystal lattice of exotic nuclei, the inner crust with its neutron drip and free neutron fluid, the nuclear pasta phases with their spaghetti and lasagna and Swiss cheese, all of this is packed into a layer about as thick as the distance from one end of a small town to the other. Walk from one end of your neighborhood to the other, and that distance represents the entire depth of the neutron star crust, within which matter transitions from something recognizably atomic to something utterly alien. This thin crust plays an enormously important role in how neutron stars behave. The crust is rigid. It's a solid crystalline structure. Unlike the fluid core beneath it, the crust can sustain stresses and strains. It can crack. And when it cracks, dramatic things happen. Neutron stars are sometimes observed to undergo sudden changes in their rotation rate. They'll be spinning at an incredibly precise, steady rate, and then abruptly, in less than a minute, their spin rate increases slightly. These events are called glitches, and they've been observed in dozens of pulsars. The leading explanation for glitches involves the crust and its relationship with the fluid beneath it. Here's the idea. As a neutron star spins, it gradually slows down over time, losing energy through electromagnetic radiation. The crust, being rigid and solid, slows down smoothly. But the neutron fluid in the inner crust and the outer core doesn't have to slow down at the same rate. It's a superfluid, and superfluids have a peculiar property. They can only rotate by forming tiny quantized vortices, discrete spinning filaments. The angular momentum of the superfluid is stored in these vortices. As the crust slows down, the vortices in the superfluid should move outward to reduce the superfluid's rotation rate. But the vortices can get pinned. They can stick to the nuclei in the crust's crystal lattice, prevented from moving by the strong nuclear force. When this happens, the superfluid doesn't slow down with the crust. It maintains its faster rotation rate. A lag builds up between the slowly spinning crust and the faster spinning superfluid beneath it. Eventually, the stress becomes too great. The pinned vortices suddenly unpin. They release their stored angular momentum into the crust. The crust suddenly speeds up. The neutron star glitches. The whole process is like a clock spring that slowly winds up and then suddenly releases. The crust is the clock mechanism. The superfluid is the spring. And the glitch is the release. These glitches are one of the best pieces of indirect evidence we have for superfluidity inside neutron stars. We'll talk more about superfluidity when we get to the core, but even here in the crust, the interaction between the rigid crystalline lattice and the superfluid neutrons creates observable effects that astronomers can study from billions of miles away. The crust also plays a role in one of the most dramatic phenomena associated with neutron stars: starquakes. Just as Earth's crust can crack and shift, producing earthquakes, a neutron star's crust can crack, producing starquakes. But the energy involved is incomparably greater. A starquake on a neutron star can release more energy in a fraction of a second than the sun emits in 100,000 years. Starquakes are thought to be responsible for some of the giant flares observed from magnetars. In August of 1998 and again in December of 2004, enormous bursts of gamma rays and X-rays were detected coming from magnetars in our galaxy. The 2004 event, from a magnetar called SGR 1806-20, released more energy in 1/10 of a second than the sun releases in 250,000 years. The burst was so powerful that it measurably affected Earth's ionosphere from about 50,000 light years away. One leading explanation is that the crust of the magnetar cracked under the stress of its enormously powerful magnetic field, releasing a torrent of energy as the field rearranged itself. All of this drama, glitches, starquakes, gamma ray bursts, nuclear pasta, exotic crystal lattices, all of it happens in a shell of matter less than 2 kilometers thick. The crust of a neutron star is thin, but it is extraordinarily rich in physics. And everything we've discussed in the crust, as exotic and extreme as it is, represents states of matter that physicists feel reasonably confident about. The physics of the outer crust is well understood. We know how crystal lattices of nuclei behave in a sea of electrons because we can study similar, though much less extreme, systems in laboratories. The physics of the inner crust is less certain, but computer simulations using established nuclear physics consistently produce the pasta phases. The details might change as our models improve, but the broad picture is probably correct. But below the crust, things change. Below the pasta layer, where the last vestiges of individual nuclei dissolve into a continuous fluid, we enter the core. And the core is where our confidence begins to waver. The core is where the neutron star holds its deepest secrets. The ones we haven't yet cracked. The outer core, the region just below the crust, is probably the best understood part of the core. It's thought to be a uniform fluid of neutrons with a small admixture of protons and electrons. This is the neutron fluid that gives neutron stars their name, and this fluid has properties so extraordinary that even after decades of study, they still challenge our understanding of quantum mechanics at the most extreme scales. That is where we are going next, into the fluid heart of the neutron star, into a realm where matter flows without friction, where magnetic fields are trapped in quantized filaments, and where the very concept of what a liquid means takes on an entirely new meaning. The outer core is where the neutron star truly begins to show us how strange the universe can be when you push matter beyond every limit we thought existed. The crust was the appetizer. The core is the main course. And the deeper we go, the more uncertain and the more fascinating everything becomes. Below the crust, below the pasta, below the last traces of anything resembling individual nuclei, you enter the outer core of the neutron star. And this is where the neutron star truly earns its name. Because the outer core is dominated by neutrons, free neutrons, not bound inside nuclei, not arranged in any lattice, not organized into any geometric shapes, just neutrons, an ocean of them, a vast continuous fluid of neutron matter that makes up the bulk of the star's volume and most of its mass. The transition from crust to core isn't a sharp boundary like the surface of a lake. It's more gradual. As you descend through the deepest pasta layers, the last distorted remnants of nuclear structure dissolve. The sheets and tubes and bubbles of nuclear matter merge with the surrounding neutron fluid until there's no distinction left. Everything becomes one uniform substance, a liquid. Not solid, not a gas, not a plasma, but a genuine quantum liquid with properties unlike any fluid you've ever encountered. The outer core extends from just below the crust at a density of roughly 200 trillion grams per cubic centimeter, down to a density of about 500 trillion to 1 quadrillion grams per cubic centimeter. In terms of physical depth, the outer core occupies a shell roughly from about 10 kilometers down to perhaps 5 or 6 kilometers from the center of the star. This means the outer core is several kilometers thick. In a neutron star only 12 or 13 kilometers in radius, the outer core constitutes the majority of the star's volume. If the crust was a thin shell wrapped around the outside, the outer core is the meat of the star, the substance, the bulk, and that substance is overwhelmingly neutrons. About 95% of the particles in the outer core are neutrons. The remaining 5% or so are protons and electrons in roughly equal numbers, maintained by the requirements of something called beta equilibrium. Let me explain what that means because it's important for understanding why the composition is what it is. In the outer core, two reactions can occur. A neutron can decay into a proton, an electron, and an antineutrino. This is ordinary beta decay, the same process that happens with radioactive atoms on Earth. A free neutron left on its own will decay this way in about 10 minutes. But the reverse process can also happen. An electron and a proton can combine to produce a neutron and a neutrino. This is the inverse beta decay we discussed earlier. the process that creates neutrons during the stellar collapse in the first place. In the outer core, both of these reactions are happening simultaneously. Neutrons are decaying into protons and electrons are combining back into neutrons. When these two rates are equal, the system is in beta equilibrium. The fraction of protons and electrons stabilizes at whatever value makes the two rates balance. Under the conditions in the outer core, beta equilibrium results in a composition of roughly 95% neutrons and 5% protons, with an equal number of electrons to maintain charge neutrality. The exact fraction depends on the density and on the details of the nuclear interactions, which is one of the things physicists are still working to pin down. But the basic picture is clear. The outer core is a neutron-dominated fluid with a small admixture of charged particles. Now, here's where things become truly remarkable. This neutron fluid isn't just any liquid. Theoretical calculations strongly suggest that the neutrons in the outer core form a superfluid. And a superfluid is one of the strangest states of matter that quantum mechanics allows. To understand what a superfluid is, you first need to understand what makes an ordinary fluid behave the way it does. When you pour water, when you stir honey, when you watch oil flow slowly down a surface, what you're seeing is the effect of viscosity. Viscosity is essentially internal friction within a fluid. The molecules in the fluid bump into each other, jostle each other, transfer momentum between different layers. This internal friction is what makes thick fluids flow slowly and thin fluids flow quickly. Honey has high viscosity, water has low viscosity, but all ordinary fluids have some viscosity. There's always some internal friction. A superfluid has zero viscosity, absolutely zero. Not very low, not approximately zero, exactly zero. No internal friction whatsoever. This isn't a technicality or a rounding error. It's a fundamental quantum mechanical state in which the fluid literally cannot experience friction. If you set a superfluid spinning in a container and then remove the container, the superfluid would continue spinning forever. Not for a very long time, not for billions of years, forever. It would never slow down because there's no mechanism for it to lose energy to friction. There is no friction to lose energy to. We know superfluids exist because we've made them in laboratories on Earth. Helium-4, when cooled to below about 2.2 degrees above absolute zero, becomes a superfluid. It displays astonishing properties. It can climb up the walls of its container, defying gravity by flowing in a thin film up and over the rim. It can flow through channels so narrow that no ordinary fluid could pass through. It conducts heat with almost perfect efficiency. These properties have been studied extensively since the 1930s and are well understood in terms of quantum mechanics. The mechanism behind superfluidity involves quantum pairing. In liquid helium, atoms pair up through quantum mechanical interactions. These pairs, called Cooper pairs in the analogous case of superconductivity, behave collectively as a single quantum entity. They all share the same quantum state. Because of this, they can't scatter off each other in the way that individual atoms can. They move together as one, flowing without any internal friction. In the outer core of a neutron star, a similar process is believed to occur with neutrons. Neutrons attract each other through the residual strong nuclear force at certain distances. This attraction, while much weaker than the force that binds quarks inside a proton or neutron, is strong enough to allow neutrons to form pairs at the extraordinarily high densities of the outer core. These paired neutrons, like the helium atoms in a superfluid, occupy the same quantum state and flow without friction. But there's an important subtlety. The pairing of neutrons in a neutron star is different from the pairing of helium atoms in a laboratory. In helium, the pairs form in what physicists call an S-wave state, meaning the paired atoms have zero relative angular momentum. In neutron star matter, particularly in the outer core, theoretical calculations suggest that the neutron pairs form in a p-wave state, specifically a state called the 3p2 channel. This means the paired neutrons orbit around each other with 1 unit of angular momentum. Why does this matter? Because the type of pairing affects the properties of the superfluid. A 3p2 superfluid has an anisotropic gap, meaning its superfluid properties are different in different directions. It's more complex than the simple isotropic superfluidity of helium-4. The details of this pairing state affect how the superfluid responds to rotation, how it interacts with magnetic fields, and how quickly it allows the neutron star to cool. The cooling of neutron stars is actually one of the key ways we can test whether superfluidity really exists inside them. When neutron pairs form, the pairing releases energy and also changes the rate at which the star can emit neutrinos, which are the primary way young neutron stars lose heat. Different pairing states produce different cooling rates. By observing how quickly real neutron stars cool and comparing those observations with theoretical models that include or exclude superfluidity, astronomers can constrain whether and how neutrons are paired. One of the most compelling pieces of evidence came from observations of the neutron star in the Cassiopeia A supernova remnant. This neutron star, known as Cass A, was formed in a supernova explosion that light from which reached Earth around 1680, making it one of the youngest known neutron stars in our galaxy, only about 340 years old. Observations with the Chandra X-ray Observatory showed that Cass A's surface temperature appeared to be dropping unusually rapidly. In 2011, a team of researchers proposed that this rapid cooling could be explained if the neutrons in the star's core had recently begun to form as superfluid. According to their model, the neutron superfluid in Cass A had just formed, switching on a new cooling mechanism that caused the rapid temperature drop. If correct, this would mean we actually observed the onset of neutron superfluidity in real time in an actual neutron star. This result is still debated. Other explanations for the cooling have been proposed, and the temperature measurements themselves have been questioned by some researchers. But the Cass A observations remain one of the most tantalizing hints that neutron superfluidity is real and not just a theoretical prediction. Now, superfluidity does something peculiar to rotation. A superfluid cannot rotate like a normal fluid. When you spin a cup of coffee, the coffee rotates smoothly, every part of the fluid turning together. A superfluid can't do this. Because of its quantum nature, a superfluid can only rotate by forming quantized vortices, tiny whirlpools each carrying exactly 1 quantum of angular momentum. Each vortex is an incredibly thin filament, only about a femtometer in diameter, roughly the size of an atomic nucleus, around which the superfluid circulates. In a neutron star spinning hundreds of times per second, the number of these vortices is enormous. A typical neutron star might contain about 10 to the 18 vortices, roughly a billion tiny quantum whirlpools threading through the superfluid core. These vortices arrange themselves in a roughly uniform array, like a forest of incredibly thin trees, each one carrying a tiny portion of the star's total angular momentum. The total rotation of the star is the sum of all these individual vortex circulations. This vortex structure is directly connected to the pulsar glitches I mentioned when we were discussing the crust. Remember, a glitch is a sudden increase in a neutron star's rotation rate. The leading model explains glitches as the sudden release of angular momentum stored in the superfluid. As the crust gradually slows down, the superfluid vortices should migrate outward to match. But vortices can become pinned to structures in the crust or flux tubes in the core. When they're pinned, angular momentum accumulates in the superfluid until the stress overwhelms the pinning force. The vortices release catastrophically, the crust suddenly speeds up, and the neutron star glitches. This is the same mechanism we just explored. But what matters here is what the glitches tell us about how much of the star is superfluid. The Vela pulsar, a neutron star about 900 light-years from Earth, is one of the best studied glitching pulsars. It experiences large glitches roughly every 3 years. Each glitch increases its rotation rate by about 1 part in a million, which doesn't sound like much until you remember that this neutron star is spinning about 11 times per second and has more mass than the Sun. The amount of angular momentum transferred in a single glitch is enormous. Calculations show that the glitches in Vela require a significant fraction of the star's moment of inertia to be in superfluid form. Specifically, at least a few percent of the star's mass must be in a superfluid that can store and release angular momentum. This is strong indirect evidence that a large portion of the neutron star's interior is indeed superfluid. Other pulsars glitch too, though with different frequencies and magnitudes. The Crab pulsar, the neutron star at the heart of the Crab Nebula, formed in the supernova of 1054, glitches more frequently, but with smaller magnitudes than Vela. The differences between glitching behaviors in different pulsars provide additional constraints on the superfluid properties inside neutron stars. Let me now turn to the protons in the outer core, because they have their own extraordinary story. While neutrons make up about 95% of the outer core, the roughly 5% that are protons are also predicted to form pairs. But protons are charged particles, and when charged particles pair up and form a condensate, the result isn't superfluidity, it's superconductivity. Superconductivity is the electrical analog of superfluidity. In a superconductor, electric current flows without any resistance. Zero resistance. Not low resistance, zero. Once a current is established in a superconducting loop, it will flow forever without any energy input. We use superconductors on Earth in MRI machines, particle accelerators, and experimental fusion reactors. All the superconductors we use on Earth need to be cooled to extremely low temperatures, usually within a few degrees of absolute zero. But the interior of a neutron star, despite being hundreds of millions of degrees hot, can still be superconducting. That sounds contradictory, but remember, temperature is relative. What matters isn't the absolute temperature. What matters is how the temperature compares to the pairing energy. The pairing energy for protons in neutron star matter is so enormous, corresponding to temperatures of billions of degrees, that the actual temperature of the neutron star's interior, which is only about 100 million to a billion degrees, is effectively cold by comparison. The protons are cold enough, in terms of their pairing energy, to be superconducting. In a superconducting neutron star core, magnetic fields can't spread smoothly through the material like they do in ordinary matter. Instead, The magnetic field is confined to thin quantized tubes called flux tubes or fluxoids. Each flux tube carries exactly 1 quantum of magnetic flux. Like the vortices in the superfluid, these flux tubes are incredibly thin, only a few femtometers in diameter. And like the vortices, there are an enormous number of them, perhaps 10 to the 30 or more, threading through the superconducting proton fluid. This has profound consequences for how the neutron star's magnetic field evolves over time. In an ordinary conductor, a magnetic field would slowly diffuse through the material, spreading out and weakening over time. This process is called ohmic dissipation, and it would cause a neutron star's magnetic field to decay relatively quickly, perhaps in a few million years. But in a superconductor, the magnetic field is locked into the flux tubes. It can't diffuse. The field is frozen into the superconducting proton fluid. This means neutron star magnetic fields can persist for much longer than they would in ordinary matter. This is consistent with observations showing that many neutron stars maintain powerful magnetic fields for millions of years. The interaction between the superfluid neutron vortices and the superconducting proton flux tubes adds another layer of complexity. The vortices and flux tubes can interact with each other. They can pin to each other, drag each other, scatter off each other. These interactions affect how the neutron star spins down, how its magnetic field evolves, and how glitches behave. The physics of this interaction is an active area of research and remains one of the more challenging aspects of neutron star theory. There's also a third component in the outer core that we haven't discussed yet: electrons. The electrons in the outer core are relativistic, moving at nearly the speed of light. They form a normal fluid, not a superfluid and not a superconductor, at least not in the conventional sense. The electrons play a crucial role in maintaining charge neutrality. For every proton in the outer core, there must be an electron to balance its positive charge. The electrons also contribute to the thermal conductivity of the core and help mediate interactions between the neutrons and protons. In some models, muons also appear in the outer core. A muon is essentially a heavier version of an electron, about 207 times more massive. At the densities found in the outer core, the electrons become energetic enough that it becomes favorable for some of them to convert into muons. This happens when the electron Fermi energy exceeds the muon rest mass energy, which occurs at about 2 times nuclear saturation density. Once muons appear, they join the electrons in maintaining charge neutrality, meaning you now have 4 species of particle in the outer core: neutrons, protons, electrons, and muons. Let me step back for a moment and consider what we're describing here. The outer core of a neutron star is a fluid made of neutrons with a small admixture of protons, electrons, and possibly muons. The neutrons form a superfluid with 0 viscosity. The protons form a superconductor with 0 electrical resistance. The magnetic field is quantized into thin flux tubes. The rotation is quantized into thin vortex lines. And all of these components interact with each other in complex ways that affect the star's observable behavior. This is a system of extraordinary complexity. And yet, compared to what might lie deeper in the star, the outer core is relatively well understood. I say relatively because there are still significant uncertainties. The exact strength of the superfluid pairing, the precise interaction between vortices and flux tubes, the detailed behavior of matter at these densities, These are all subjects of active research and debate, but the basic picture, a superfluid of neutrons coexisting with a superconductor of protons in a sea of relativistic leptons, is supported by both theoretical calculations and observational evidence. Most neutron star physicists would agree on this broad description of the outer core, even if they disagree on the details. This relative confidence comes from the fact that the densities in the outer core, while extreme, are not completely beyond our theoretical reach. The outer core exists at densities of roughly 1 to 3 times the density of nuclear matter. Nuclear matter is the stuff inside an atomic nucleus, and we can study nuclear matter in laboratories. We can smash nuclei together in particle accelerators and measure the properties of nuclear matter at these densities, at least briefly and at high temperatures. Theoretical models of nuclear interactions have been tested against decades of experimental data from nuclear physics laboratories. While these models aren't perfect, they give us a reasonable foundation for understanding the outer core. The situation is analogous to understanding the ocean. We know what water is, we know its properties, we can study it in laboratories. So even though the deep ocean is an extreme environment with crushing pressures and total darkness, we understand the basic physics well enough to make confident predictions about what water does down there. The outer core is similar. We know what neutrons are, we know how they interact. We can study nuclear forces in laboratories. So even though the outer core is an extreme environment far beyond anything we can create on Earth, we understand the basic physics well enough to make reasonably confident predictions about how neutron matter behaves there. But this confidence has a limit, and that limit is a density of roughly 2 to 3 times the density of nuclear matter. Above that threshold, which corresponds to the transition from the outer core to the inner core, our theoretical models become increasingly uncertain. The interactions between particles become more complex. New particles might appear. The fundamental nature of matter itself might change. We start to lose our footing. At the densities of the outer core, the neutrons and protons are distinct particles, identifiable as individual objects with well-defined properties. Each neutron contains 3 quarks, 2 down quarks, and 1 up quark, bound together by gluons, the carriers of the strong nuclear force. Each proton contains 3 quarks, 2 up quarks, and 1 down quark, similarly bound. The quarks are confined inside the neutrons and protons. They can't escape. They can't roam free. This confinement of quarks is one of the fundamental features of the strong force. But confinement isn't absolute. We know from laboratory experiments that extremely high temperatures and densities, quarks can become deconfined. They can break free from the protons and neutrons that contain them and exist as free particles in a state called a quark-gluon plasma. This has been observed in particle accelerator experiments at the relativistic heavy ion collider at Brookhaven National Laboratory and at the Large Hadron Collider at CERN. When gold nuclei or lead nuclei are smashed together at nearly the speed of light, the resulting fireball briefly reaches temperatures and densities high enough to free the quarks. For a fleeting instant, a tiny volume of quark-gluon plasma exists before it cools, and the quarks recombine into ordinary particles. In the outer core of a neutron star, the density is high, but perhaps not high enough for deconfinement. The quarks remain locked inside their neutrons and protons. The identity of these particles is maintained. But as you approach the inner core, As the density climbs higher and higher, the particles are squeezed closer and closer together. At some point, the neutrons and protons are so tightly packed that they overlap. The quarks inside one neutron start to mingle with the quarks inside neighboring neutrons. The boundaries between particles blur, and at that point, something fundamental might change. The quarks might break free entirely, creating a new state of matter unlike anything in the outer core. But I'm getting ahead of myself. That's a story for the innermost core. For now, let's appreciate the outer core for what it is. A quantum fluid of staggering complexity, governed by the interplay of superfluidity, superconductivity, and strong nuclear interactions, occupying the bulk of the neutron star's interior and generating observable phenomena that astronomers can study from across the galaxy. The outer core is where the neutron star's heartbeat lives. It's where the superfluid stores the angular momentum that's released in glitches. It's where the superconductor locks in the magnetic field that drives the pulsar emission. It's where the bulk of the star's mass resides, providing the gravitational field that curves space and slows time around the neutron star's surface. And in many ways, the outer core represents the boundary of our knowledge. Everything above it, the atmosphere, the outer crust, the inner crust, the pasta layers, the outer core itself, all of this is territory where physicists feel they have at least a reasonable handle on the physics. The models might not be perfect. The details might shift as our understanding improves. But the broad strokes are probably right. We understand these regions well enough to make testable predictions and to compare those predictions meaningfully with observations. Below the outer core, everything changes. The density exceeds anything we can study or reproduce in any laboratory on Earth. The theoretical models diverge. Different research groups predict wildly different behaviors for matter at these extreme densities. Some say the neutrons persist, just packed even more tightly. Others say new exotic particles appear. Others say the neutrons dissolve entirely. They're quarks and spilling out into a fundamentally new phase of matter. And others propose states so exotic that they challenge our understanding of quantum chromodynamics itself. The theory that describes how quarks and gluons interact. The inner core is where neutron star physics goes from challenging to genuinely unknown. It's where confident predictions give way to competing hypotheses. It's where the biggest open questions in fundamental physics collide with the most extreme environment in the observable universe. The outer core, beautiful and complex as it is the last region where we feel the ground beneath our feet. Below it lies the inner core. And the inner core is where we enter the true unknown. The place where the laws of physics themselves might take forms we haven't yet imagined. Where the matter crushed at the center of a dead star might reveal something fundamental about how the universe works at its deepest level. Something we've been trying to understand for decades, but haven't yet cracked. That's what's waiting for us now. Now we descend into the center, the innermost core of the neutron star. And this is where everything we think we know starts to unravel. Because the inner core is the region where the density exceeds anything we can reproduce, anything we can simulate with full confidence, and anything we can test directly in any laboratory ever built on Earth. The inner core is where physics reaches the edge of its understanding. And what lies there might be one of the most important unsolved questions in all of science. The inner core begins where the density climbs above roughly 2 to 3 times the density of normal nuclear matter. Nuclear saturation density, The density inside an ordinary atomic nucleus is about 230 trillion grams per cubic centimeter. In the outer core, the density is 1 to 3 times this value. But at the center of a neutron star, the density can reach 5 to 8 times nuclear saturation density. Some models predict even higher. We're talking about densities of 1 to 2 quadrillion grams per cubic centimeter. Matter compressed so far beyond nuclear density that the particles themselves might not survive intact. Let me put this in perspective one more time. At nuclear saturation density, neutrons and protons are touching. They're packed as tightly as they exist inside an atomic nucleus. This is already the densest form of matter we can study in laboratories. Everything beyond this point is extrapolation. We're using theories that were developed and tested at lower densities and extending them into a regime where we can't directly verify whether they still work. It's like using a map that's accurate for your city and hoping it still works when you drive into unmapped territory. Maybe it does, maybe it doesn't. You won't know until you get there. And we haven't gotten there yet. The fundamental question about the inner core is simple to state, but extraordinarily difficult to answer. What happens to neutrons when you squeeze them beyond the point where they're already touching? In the outer core, neutrons are distinct particles. Each one is a bound state of 3 quarks, 2 down quarks, and 1 up quark, held together by gluons, the force carriers of the strong nuclear force. The quarks inside a neutron are confined. They cannot escape. This confinement is a fundamental property of the strong force. Under normal conditions, you simply cannot have a free quark. Quarks are always bound inside hadrons, the family of particles that includes protons and neutrons. If you try to pull a quark out of a proton, the energy you put into the attempt creates new quarks from the vacuum, which immediately bind with the original quarks to form new hadrons. The quark never gets free. This is one of the most remarkable features of the strong force, and it's been confirmed by decades of experiments in particle physics. But confinement might not be absolute. If deconfinement occurs inside neutron stars, the inner core wouldn't be made of neutrons at all. It would be made of free quarks swimming in a sea of gluons, a state of matter called quark matter. The neutrons would have dissolved. Their identity would have been erased just as atomic identity was erased when atoms collapsed into neutrons in the first place. This would be another level of structural destruction. Atoms dissolved into neutrons in the crust, and now neutrons themselves might dissolve into quarks in the core. This is one of the leading hypotheses for the inner core, but it's far from the only one. Let's walk through the major possibilities that physicists have proposed, because the honest truth is that we don't know which one is correct. We might not know for decades, and it's possible that the real answer is something nobody has thought of yet. The first possibility is that nothing exotic happens. In this scenario, the inner core is simply a denser version of the outer core. More neutrons packed more tightly together with a slightly higher fraction of protons and electrons, but no fundamentally new physics. The neutrons remain intact. No new particles appear. The matter is just very, very dense nuclear matter. This is the conservative option, and some models of the nuclear force support it. If the repulsive core of the neutron-neutron interaction is strong enough at short distances, it could prevent the neutrons from overlapping enough for anything exotic to occur. The neutrons would resist being crushed any further, held apart by the hard repulsive core of the strong force, and the matter would remain fundamentally the same as in the outer core, just compressed more. This scenario is simple and clean, but many physicists consider it unlikely for the densest neutron stars. The densities at the center are so extreme that it seems improbable that nothing new would happen. At 5 to 8 times nuclear density, the neutrons are so compressed that they overlap significantly. The quarks inside neighboring neutrons are practically on top of each other. It would be surprising if this overlap didn't produce new phenomena. The second possibility involves hyperons. These are baryons, particles in the same family as protons and neutrons, but containing one or more strange quarks. A neutron contains 2 down quarks and 1 up quark. A proton contains 2 up quarks and 1 down quark. But there are other possible combinations. A lambda hyperon contains 1 up quark, 1 down quark, and 1 strange quark. A sigma hyperon contains different combinations of up, down, and strange quarks. A cascade hyperon, also called a Xi particle, contains 1 or 2 strange quarks paired with up or down quarks. Under normal conditions, hyperons are unstable. They decay in about a 10 billionth of a second, transforming back into protons, neutrons, and lighter particles. You can't accumulate a pile of hyperons on your desk. They vanish almost as soon as they're created. But inside the inner core of a neutron star, the rules are different. At these extreme densities, the Fermi energy of the neutrons, the quantum mechanical energy associated with being squeezed into a small space, becomes very high. So high that it becomes energetically favorable for some neutrons to transform into hyperons, even though hyperons are heavier. The conversion reduces the total energy of the system because it relieves the Fermi pressure. Each hyperon that forms removes a neutron from the increasingly crowded neutron population, reducing the pressure. It's like releasing pressure from an overcrowded room by moving some people to an adjacent, emptier room. Even though the adjacent room might have a higher floor, so to speak, because hyperons have greater mass, the overall energy of the system decreases because the overcrowding is reduced. Many theoretical models predict that hyperons should appear in the inner core of neutron stars once the density exceeds about 2 to 3 times nuclear saturation density. Lambda hyperons would appear first, followed by sigma minus hyperons and possibly cascade hyperons at even higher densities. If this is correct, the inner core of a neutron star isn't made entirely of neutrons. It is a mixed fluid of neutrons, protons, electrons, muons, and various species of hyperons, all coexisting in beta equilibrium. But here's the problem. This seemingly reasonable prediction creates what physicists call the hyperon puzzle, and it's one of the most vexing problems in neutron star physics. The issue is this. When hyperons appear, they soften the equation of state. In physics, the equation of state is the relationship between the pressure and density of matter. A stiff equation of state means that pressure increases rapidly with density, which supports a more massive neutron star against gravitational collapse. A soft equation of state means pressure increases more slowly, which means the star can't hold up as much mass before collapsing into a black hole. The maximum mass a neutron star can have before it collapses into a black hole depends critically on the equation of state. When hyperons appear, they take energy away from the neutrons, reducing the overall pressure at a given density. This softens the equation of state. And when the equation of state softens, the maximum mass that a neutron star can sustain decreases. Most models that include hyperons predict a maximum neutron star mass of about 1.5 to 1.7 solar masses. The problem is that we've observed neutron stars more massive than this. In 2010, a neutron star designated PSRJ 1614 minus 2230 was measured to have a mass of about 1.97 times the mass of the Sun. Since then, even heavier neutron stars have been found. PSRJ 0348 plus 0432 has a mass of about 2.01 solar masses. And in 2022, a neutron star was measured at roughly 2.35 solar masses, though this measurement has larger uncertainties. These massive neutron stars shouldn't exist if the equation of state is softened by hyperons. The presence of hyperons would make the star too soft to support that much mass. The star should have collapsed into a black hole long before reaching 2 solar masses. And yet, these massive neutron stars are there. They exist. We've measured them. This is the hyperon puzzle. Theory says hyperons should appear at the densities inside massive neutron stars. But if hyperons appear, those stars shouldn't be able to exist at the masses we've observed. Something is wrong. Either hyperons don't appear when we think they should, or something else provides the additional pressure needed to support these massive stars, even in the presence of hyperons. Solving this puzzle would tell us something fundamental about how the strong force works at extreme densities. And right now, we don't have a definitive answer. Several solutions have been proposed. One is that additional repulsive interactions between hyperons, interactions that aren't included in the simplest models, provide extra pressure that stiffens the equation of state. If hyperons repel each other strongly enough at short range, they could appear without softening the equation of state as much. Some calculations, including these additional repulsive interactions, can produce maximum masses above 2 solar masses even with hyperons present. But these calculations require assumptions about hyperon-hyperon interactions that we can't test directly in laboratories. Another proposed solution brings us to the third possibility for the inner core: quark deconfinement. Perhaps the reason the hyperon puzzle exists is that hyperons don't actually survive in the densest regions. Perhaps before the density gets high enough for hyperons to cause problems, the matter undergoes a phase transition. The neutrons and any nascent hyperons dissolve into their constituent quarks. The matter transitions from hadronic matter, made of distinct baryons like neutrons and protons and hyperons, to quark matter, made of free, deconfined quarks. If this happens, the inner core of the neutron star would be a quark core, a region of matter where quarks are no longer confined inside individual particles, but exist freely in a continuous medium of quarks and gluons. This is sometimes called quark-gluon plasma, though the conditions inside a neutron star are quite different from the quark-gluon plasma created in particle accelerators. In accelerators, the deconfined matter is extremely hot, trillions of degrees, and exists for only a fleeting instant. In a neutron star, the deconfined matter would be relatively cold, sustained by pressure rather than temperature, and it would exist in stable equilibrium for millions or billions of years. The quark matter in the inner core, if it exists, would likely consist of 3 flavors of quark: up quarks, down quarks, and strange quarks. Under normal conditions, strange quarks are heavier than up and down quarks and are unstable. But at the densities of the inner core, just as it can become energetically favorable to produce hyperons, it can become energetically favorable to produce strange quarks. The resulting 3-flavor quark matter is sometimes called strange quark matter. There's an even more speculative idea associated with strange quark matter. In 1984, physicist Edward Witten proposed that strange quark matter might be the true ground state of matter. In other words, it's possible that matter made of roughly equal numbers of up, down, and strange quarks at zero pressure is actually more stable than ordinary nuclear matter. If this is true, then a lump of strange quark matter wouldn't just exist under extreme pressure. It would be stable all by itself. This is called the strange matter hypothesis, and if it's correct, it would have astonishing implications. Neutron stars might not be neutron stars at all. They might be strange stars, objects made entirely or almost entirely of strange quark matter, held together by the strong force rather than gravity. A strange star would look very different from a conventional neutron star in certain respects. It would have a sharper surface, no crust in the traditional sense, and different cooling properties. Most physicists consider the strange matter hypothesis unlikely, but it hasn't been ruled out. The fundamental problem is that we can't calculate the energy of strange quark matter from first principles with enough precision to determine whether it's more or less stable than nuclear matter. The calculations involve quantum chromodynamics at strong coupling, which is notoriously difficult. Until we can solve QCD at these densities, the strange matter hypothesis remains an open question. Even without the strange matter hypothesis, the idea of a quark matter core inside an otherwise normal neutron star is taken seriously by many researchers. In this picture, the neutron star would have a layered structure, a crust of nuclei and electrons at the surface, an outer core of superfluid neutrons and superconducting protons, and an inner core of deconfined quark matter. The transition from hadronic matter to quark matter could be sharp, a first-order phase transition like the transition from liquid water to ice, or it could be gradual, a smooth crossover where matter continuously transforms from one phase to the other. If the transition is sharp, there might be a distinct boundary inside the neutron star, where neutrons abruptly dissolve into quarks. This boundary would be like an interior surface, separating two fundamentally different phases of matter. A neutron star with such a boundary would have measurably different properties from one without it. The radius, the tidal deformability, the cooling rate, all of these would be affected by the presence of a quark core. And these differences might be detectable. This brings us to one of the most exciting developments in neutron star physics: gravitational wave astronomy. In 2017, the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars, an event designated GW170817. This was the first time gravitational waves from a neutron star merger were detected. The signal contained information about how the neutron stars deformed as they spiraled toward each other in their final moments. This deformation, called tidal deformability, depends on the equation of state. A stiffer equation of state produces a larger tidal deformation. A softer one produces a smaller deformation. The GW170817 observations placed constraints on the tidal deformability of neutron stars, which in turn constrained the equation of state. The results ruled out the very stiffest equations of state, but were also inconsistent with the very softest ones. The data pointed toward a moderately stiff equation of state, one that allows neutron stars to reach about 2 solar masses, but doesn't make them too large. These constraints don't yet distinguish definitively between the different scenarios for the inner core. A purely hadronic equation of state with no exotic matter can fit the data. So can an equation of state with a quark matter core. So can models with hyperons if additional repulsive interactions are included. The current gravitational wave data narrow the possibilities, but don't pinpoint the answer. Future observations of neutron star mergers with improved detector sensitivity are expected to provide much tighter constraints. The next generation of gravitational wave detectors, including upgrades to LIGO and new facilities like the Einstein Telescope planned for Europe and Cosmic Explorer proposed for the United States, should be able to measure tidal deformability with enough precision to distinguish between competing models. Beyond quark matter, there are even more exotic possibilities that have been proposed for the inner core. One is a state called a color superconductor. In ordinary superconductivity, electrons form pairs called Cooper pairs that conduct electricity without resistance. In color superconductivity, quarks form analogous pairs, but quarks carry a property called color charge, which is the strong force equivalent of electric charge. Color charge comes in 3 types, whimsically named red, green, and blue. In a color superconductor, quarks of different colors pair up, forming a condensate that has distinctive properties. There are several possible phases of color superconducting quark matter, depending on which quarks pair with which. In the color flavor locked phase, all 3 flavors of quark pair, with all 3 colors in a particularly symmetric way. This phase is theoretically well understood and is predicted to be the ground state of quark matter at asymptotically high densities. Densities so extreme that the strong coupling constant becomes small and calculations become reliable. Whether the densities inside real neutron stars are high enough to reach this phase is unknown. The densities might be in a regime where the calculations are neither simple enough for reliable perturbative methods nor manageable by current lattice QCD simulations. Another proposed state is a Bose-Einstein condensate of kaons. Kaons are mesons, particles made of a quark and an antiquark. Specifically, one strange quark paired with an up or down antiquark, or vice versa. Under certain conditions in dense matter, kaons might form a condensate, a state where a macroscopic number of kaons occupy the same quantum state. A kaon condensate would affect the equation of state and the cooling properties of the neutron star in distinctive ways. There have also been proposals involving pion condensates and delta baryon matter. Each represents a different theoretical prediction for what happens at the most extreme densities, and each would produce a neutron star with slightly different observable properties. The variety of proposals alone tells you something important. When physicists propose this many competing explanations for the same phenomenon, it's a sure sign that nobody knows the answer yet. Let me linger on color superconductivity because it deserves more than a passing mention. In an ordinary superconductor on Earth, electrons form pairs that move through the metal lattice without scattering, conducting electricity with zero resistance. The pairing happens because of a subtle attractive interaction between electrons, mediated by vibrations in the crystal lattice. This attraction is incredibly weak, which is why superconductors need to be cooled to extreme cold. In color, superconducting quark matter. Something analogous happens with quarks instead of electrons. Quarks attract each other through the strong force, which is far more powerful than the lattice-mediated attraction between electrons. The energy gap associated with color superconducting pairs could be tens or even hundreds of millions of electron volts. corresponding to pairing that could survive at temperatures of trillions of degrees. The interior of a neutron star, at merely hundreds of millions of degrees, would be frigidly cold by comparison. If quark matter exists in the inner core, it's almost certainly color superconducting. The color flavor locked phase is the most symmetric version. All 9 possible combinations of 3 quark colors and 3 quark flavors participate in pairing. The result is simultaneously a superfluid and a superconductor. It breaks the symmetry of the strong force in a pattern that's mathematically analogous to how the Higgs mechanism gives masses to particles in the Standard Model. But this phase is only guaranteed to be correct at asymptotically high densities, densities so extreme that calculations become trustworthy. The cores of real neutron stars sit in between, too high for nuclear models to be reliable, too low for quark models to be reliable. We're in a theoretical no man's land. The strange matter hypothesis also deserves a closer look. If strange quark matter is truly the ground state of matter, then any sufficiently large lump of ordinary matter contacting strange matter would be converted. The strange matter essentially eating normal matter quark by quark. A neutron star, if a seed of strange matter formed in its core, would be converted entirely into a strange star. The conversion would propagate outward from the core like a burning front, transforming the entire star in seconds or minutes. A strange star would be fundamentally different from a conventional neutron star. Its surface would be sharply defined, with density dropping from nuclear density to 0 in just a few femtometers, rather than the gradual transition through a kilometer-thick crust. Its mass-radius relationship would follow a different curve. Small strange stars could be much smaller than conventional neutron stars of the same mass. These differences are in principle observable, and astronomers are actively looking for neutron stars with properties that might hint at a strange quark composition. Some physicists have speculated about nuggets of strange matter, called strangelets, drifting through space. If the hypothesis is correct, violent events involving strange stars could eject small lumps into the interstellar medium. These strangelets would be extraordinarily dense and stable, surviving indefinitely. Experiments at particle accelerators and cosmic ray detectors have looked for strangelets and found nothing, which constrains how common they can be. Most physicists consider the strange matter hypothesis unlikely, but not ruled out. The honest summary is this. We know that the inner core contains matter at 5 to 8 times nuclear saturation density. We know the fundamental theory governing this matter is quantum chromodynamics, but QCD is extraordinarily difficult to solve at these densities. The coupling constant is too large for perturbative methods, and the system is too dense and cold for current lattice QCD simulations. We're stuck in a regime where our most powerful theoretical tools don't work well. We're forced to rely on models, approximations, and extrapolations. Different models give different answers. Some predict a purely hadronic core. Some predict hyperons. Some predict quark matter. Some predict color superconductivity. Some predict sequences of transitions, where matter passes through multiple exotic phases as density increases toward the center, like geological strata but with each layer representing a fundamentally different state of matter. Without the ability to solve QCD directly at these conditions, we cannot determine which model is correct from theory alone. We need observations. And this is why neutron star observations have become so important to fundamental physics. Neutron stars are the only objects in the universe where matter exists at these densities in a cold, stable equilibrium for long periods of time. They are natural laboratories for studying Q, CD at strong coupling and high density. Every measurement of a neutron star mass, radius, cooling rate, spin behavior, gravitational wave signal, or electromagnetic emission provides another piece of the puzzle. Each observation constrains the equation of state a little more, ruling out some models and supporting others. The NICER instrument aboard the International Space Station has been measuring the radii of neutron stars by observing the X-ray emission from hotspots on their surfaces. These measurements, combined with mass estimates from pulsar timing, give us mass-radius pairs for specific neutron stars. The mass-radius relationship is directly determined by the equation of state, so every new measurement constrains the possible compositions of the inner core. Future gravitational wave observations from neutron star mergers will provide even stronger constraints. When two neutron stars merge, the gravitational wave signal contains information about the tidal deformability of both stars, which depends on their internal structure. The post-merger signal, the gravitational waves emitted by the hot, dense remnant after the two stars collide, contains even more information. This signal is at higher frequencies than current detectors can easily measure, but next-generation detectors should be able to capture it. The post-merger signal might directly reveal whether a phase transition to quark matter occurs during the merger, because such a transition would leave a distinctive imprint on the gravitational wave signal. Radio pulsar timing is another powerful tool. By precisely measuring the arrival times of radio pulses from pulsars over years or decades, astronomers can determine the masses of neutron stars in binary systems with extraordinary precision. The discovery of two solar-mass neutron stars through pulsar timing was one of the most important results in neutron star physics, immediately ruling out many soft equations of state. There are also ongoing efforts to detect gravitational waves from isolated spinning neutron stars. If a neutron star has even a tiny mountain on its surface, or if its interior has some asymmetry, it will emit continuous gravitational waves as it spins. The amplitude of these waves depends on the size of the asymmetry, which depends on the strength of the crust, and possibly on the properties of the core. Detecting or placing upper limits on these continuous waves provides additional constraints on the neutron star's internal structure. Neutrino observations from a future nearby supernova could also help. When a neutron star forms in a supernova, it emits an enormous burst of neutrinos. The properties of these neutrinos, their energies, their arrival times, their flavor composition depend on the conditions inside the newly formed neutron star, including the composition of the core. If a supernova occurs close enough to Earth, within our galaxy or a nearby galaxy, modern neutrino detectors could measure the neutrino signal in exquisite detail, providing a direct window into the physics of matter at extreme densities. We are living in a golden age of neutron star physics. The combination of gravitational wave astronomy, X-ray observations, radio pulsar timing, and theoretical advances is converging on the answer to this question. The inner core of a neutron star will not remain mysterious forever. The tools we need to solve this puzzle are being built, launched, and refined right now. Within the next 10 to 20 years, we might finally know what matter becomes at the highest densities the universe allows before a black hole forms. And that's what makes this question so profound. The inner core of a neutron star represents the last frontier of matter. Below these densities, matter exists in forms we can study in laboratories. Above these densities, matter collapses into a black hole and disappears from the observable universe entirely. The inner core of a neutron star occupies a narrow window of density between normal matter and the total gravitational collapse that produces a black hole. It's the densest form of matter that can exist without being swallowed by its own gravity. Whatever is there, whether it's hyperons, deconfined quarks, color superconductors, or something we haven't imagined yet, it represents the ultimate state of matter. The final answer to the question of what stuff becomes when you squeeze it as hard as the universe allows. We started this journey at the surface of a neutron star, where thin atmospheres of hydrogen glow in X-rays. We descended through the outer crust, where exotic nuclei form crystal lattices in a sea of relativistic electrons. We passed through the neutron drip line into the inner crust, where nuclear pasta takes shapes named after Italian food and matter forms what might be the strongest material in the universe. We crossed into the outer core, where a quantum ocean of superfluid neutrons and superconducting protons fills the bulk of the star. And finally we arrived at the inner core, where the density exceeds anything we can reproduce on Earth, and the true nature of matter remains unknown. Each layer told us something about what matter becomes under extreme conditions. Each layer pushed the boundaries of physics a little further, and each layer reminded us that the universe is stranger, more complex, and more beautiful than we might expect. The inside of a neutron star is not just a physics problem. It's a story about the nature of matter itself. About what happens when you take the stuff that makes up everything you've ever touched, everything you've ever seen, and crush it beyond recognition. Atoms become neutrons. Neutrons might become quarks, and quarks might form states of matter that haven't existed freely since the first microsecond after the Big Bang. All of this packed into a sphere smaller than a city, weighing more than the sun, spinning hundreds of times per second, with a magnetic field 1 trillion times stronger than Earth's. The inside of a neutron star is one of the most extreme environments in the observable universe. And the fact that we can study it at all, from billions of kilometers away, using telescopes, gravitational wave detectors, and the power of theoretical physics, is a testament to what human curiosity can achieve. We cannot go there, we cannot touch this matter, we cannot recreate these conditions, but we can think about them, we can calculate, we can observe, and piece by piece, measurement by measurement, we are assembling the answer to one of the deepest questions physics has ever asked. What is matter really made of when you strip away everything familiar and push it to the very edge of existence? We don't have the complete answer yet, but we're closer than we've ever been. And the answer, when it comes, will tell us something fundamental, not just about neutron stars, but about the universe itself, about the forces that hold matter together, about the laws that govern the smallest particles, about the nature of reality at its most extreme. The inside of a neutron star is one of the last great mysteries of the physical world. And it's a mystery that's within our reach to solve. That's what's hiding inside a neutron star. Not just dense matter, not just compressed atoms, but a layered world of progressively stranger states. From crystal lattices to quantum pastas, to superfluid oceans, to an unknown core that might contain forms of matter unseen anywhere else in the cosmos. An object the size of a city, holding more mass than the sun, containing within it some of the deepest unanswered questions in all of physics. And every time a pulsar flashes, every time two neutron stars spiral together and merge, every time an X-ray telescope catches the faint glow from a distant neutron star surface, the universe is giving us another clue, another piece of the puzzle, another whisper about what matters truly becomes when everything we know is crushed out of existence. We just have to keep listening.